Yes. So if you have any questions, please raise your hand or type it in the chat. I will be monitoring questions. And again, sorry for the delay. Without further ado, we're very happy to have Jyun-Jie Liao here on TCS Plus to let us know about recent progress on Marton's conjecture, also known as the PFR conjecture. And this is the last talk of this season on TCS Plus, so really looking forward to it and to having more of that next semester. Thank you.
Okay, thanks for the introduction. So this will be a survey talk for some recent progress on Marton's conjecture, and especially the proof by Gowers, Green, Manners, and Tao. Okay, so the Marton's conjecture is about a problem called the inverse sumset problem, which is defined as follows. So if we are given two sets A and B, then we define the subset of A and B to be the set that consists of all the elements that can be represented as like one element from A plus another element from B. And if we consider the case that A is a subset of F2N, then we can see that if A is an affine subspace, then this implies that the subset of A with itself will have the same size, and the converse is also true. But when we only have the guarantee that the subset of A with itself is slightly larger than the size of A, but not exactly the same as the size of A, then the problem becomes trickier. And ideally, we still want to prove some sort of inverse sumset theorem, which says that if the size of A plus A is at most k times the size of A, then we still want to claim that A is somewhat close to a subspace. And we'll call this K the doubling constant of A. Okay, so we can see the first example of a set with a small doubling constant, which is a random subset of some subspace. So if we consider a subspace V and take a random subset of A of V, which has density 1 over K, then we can see that A plus A is roughly the whole subspace V. So the doubling constant of A is exactly K. And in this case, we have a really nice property, which is that the span of A also has size roughly K times A. So a natural candidate is for the notion close to being a subspace would be the size of the span of A is at most, say, is not much larger than the size of A. But and there's a second example of a set with small doubling, which is the union of many translates of the subspace. Say if we take a subspace V and consider some 2k different random translates of V, then we can, in this case, A plus A would also be some like roughly k squared, 2k squared translates of V, and A plus A would also have size roughly K times A. But in this case, the span of A would have a much larger size, which is basically, so the span of A is basically the subspace V plus the span of this shift, and this would have size roughly 2 to the 2k times the size of A. So if we want to still make the claim that A is like a large a really dense subset of its span, then the bound we can get will be much worse, and it becomes exponential in K. But it is still independent of the size of A, which is at least a good news. And it turns out that we can actually prove some theorem in this form, which is called the Freiman-Ruzsa theorem. So it's a theorem proved by Ruzsa that is an analog of some older classic theorem by Freiman that works in the integer. So the Freiman-Ruzsa theorem says that if we have set A in F2N, which has doubling constant K, then it turns out that the size of the span of A will be bounded by 2 to the poly k times the size of A. And we have seen from our second example, which is the union of translate of a subspace, that like the span of A needs to be exponential k times the size of A. And this result have been improved by some subsequent work, and eventually Evan Zohar proved that the span of A is at most like roughly 2 to the 2k over k times the size of A. And this bound is tight by our second example. And so this exponential bound, while it does not depend on the size of A and also not on, say, the dimension, but it is not good enough for many applications. But because of our second example, this bound cannot be further improved. So if we want to get a better bound, then we need to consider some weaker statement. So a conjecture by Marton, which is widely known as the Polynomial Freiman-Ruzsa conjecture, states that if we don't require the span of A to have, if we don't consider the size of the span of A, but instead we just consider a dense subset A prime of A, and we just want the size of span of A prime to be small, then we could potentially do much better. And it is conjectured by Marton that we can potentially find a set A prime that has density 1 over poly k in A, such that the size of the span of A prime is at most poly k times larger than the size of A prime. And because the loss here is only polynomially in the doubling constant, so this is also called the Polynomial Freiman-Ruzsa conjecture. And we can see that by considering a subset of A instead of the whole set, our second example is no longer a bad example, because for the case that we have many different translate of the same subspace, we can just take one of the subspace, and we take this set to be A prime, and the span of A prime is has the same size as A prime, which is really good. And there is another equivalent form of this conjecture, which you might see in like many paper, including the recent one by GGMT, which says like we can also state that A can be covered by poly k translates of some subspace V that have size at most the size of A, and the exponent is only off by I think off by 1. And it's equivalent to the conjecture that I listed above here. Okay, and there were some progress on. So the progress on PFR is roughly as follows. So the PFR conjecture states that we want to find some subset A prime such that the density of A prime is 1 over poly k, and the span size of A prime is also 1, like poly k times larger than A prime. And the Freiman-Ruzsa theorem says that the loss would be 2 to the poly k instead of poly k. But there were some other results which show that by considering the subset A prime instead of the whole set, we can actually get the sub-exponential bound, which is something that we cannot get with the Freiman-Ruzsa theorem. And then a surprising result by Sanders shows that we can actually get a quasi-polynomial bound. And although this is not quite a polynomial as what was conjectured, it is already good enough in many TCS applications. And there was a really nice survey written by Shahar, if you are interested in Sanders' results. And very recently, in 2023, a breakthrough result by Gowers, Green, Manners, and Tal proved that PFR is actually true for constant C being 11. So it's a pretty nice result. Like we know that PFR is true, and it's actually for like a reasonably small constant instead of something crazy. And I also made some like small technical improvement that improve the constant exponency to 8. Okay, and there is also another version of PFR. We can also consider PFR over the modulo M group. And it was also conjectured that for this case, we can also get a similar result for some constant exponency that depend on the group size M. Sorry, depends on the torsion M, but not on the size of A and other things. And a recent result by Gowers, Green, Manners, and Tao also proved that PFR is true over ZMN, and for the constant C being M cubed. And more generally, the same claim would hold for any abelian group that has a torsion M, which means for every element G in the group, M times G is 0. And there is some other version of PFR over integer instead of bounded torsion abelian group, and that conjecture remains open. And it seems like the technique by GGMT cannot work for that case. Okay, so in the remaining part of this talk, I will first discuss some applications of PFR in theoretical computer science. And then after that, I will go through the proof of PFR in the case of F2 by Gowers, Green, Manners, and Tao. And I will also try to sneak in my small technical idea that improves the constant exponent, if we have time. Okay, and the most classic application of PFR in TCS is probably for linearity testing. So there's a classic BLR test which says that if we want to check whether a function f is actually a linear map, then we can randomly sample a point x and independently sample another point y, and then check whether fx plus fy equals to fx plus y. So for this test, we only need to make 3 queries. And it's pretty obvious that for any linear map, it will pass this test with 100% probability. But we will also want to prove some kind of soundness claim, which says that if we have some function that passes the test with some good enough probability, then this function should be somewhat close to a linear function. And there were some results for the 99% regime, which is for function that pass the test with really high probability. And there was also a result for the 1% regime, which is for a function that pass a BLI test with only a small epsilon probability. But the probability of passing is still greater than 0. And the result by Samorodinsky says that if we have some function that passes the BLI test with positive probability epsilon, then there exists another positive probability delta and a linear function g, such that the probability of f being consistent with g on a random input is at least delta. And so it turns out that PFR is actually equivalent to a bound for this 1% soundness for BLR test. And in particular, PFR is true if and only if we can take this delta to be polynomial in the success probability epsilon. And so next we will show how PFR implies this claim, and we will take this chance to introduce the best friend of PFR in the applications, which is the BSG theorem. So the Balog-Zamredi-Gowers theorem states that if we have some set A that doesn't necessarily have a small doubling, but if it approximately have small doubling, which means if we take a random element A1 and another independent random element A2, both from A, and then there is a noticeable probability epsilon such that A1 plus A2 falls in some set C, which is not much larger than A, then we can actually like zoom in and like find a subset A prime of A, such that A prime actually has small doubling. And also A prime is dense. A prime is also dense, and it has size at least poly epsilon times the size of A. And so this BSG is really, the BSG theorem is really useful in applications, because usually we don't necessarily have a set A that has a small doubling, but in many cases we can find some like set that approximately has a small doubling, like what we have in this condition. And then the BSG theorem would automatically give a set A prime that actually has small doubling. So the argument goes like, we start with A that has statistically has a small doubling, which means we randomly pick A1 and A2, and then the sum, and with the noticeable probability epsilon, A1 plus A2 falls in some small set. And then we apply BSG theorem to show that there exists a prime that actually has small doubling. And then with a set that has small doubling, we can apply PFR to show that there is another subset, say A double prime of A prime, that has a small span, or in other words, A double prime is a dense subset of some subspace. And because for both BSG theorem and the PFR theorem, we only have polynomial laws. So in the end, we will get a subset A double prime such that the size of A double prime is at least poly epsilon over K times the size of A. And the size of the span of A prime is also at most poly K over epsilon times the size of A prime, A double prime. And so by like throughout this procedure, we get a much stronger structure, but we are not losing much. Okay, so with the BSG theorem, we can prove the linearity testing result as follows. So our guarantee is that we have some function f that tests the BOR test with epsilon probability. Then we can define a set A, which is consists of the input-output pair of f, which is the like x concatenated with fx. And then we can see that the probability of BOR succeeds actually equals to the probability of taking a random element A and another random element of A, and then take their sum and get the, and then like the BOR test whether like fx plus y equals to fx plus fy. So BOR succeeds means the sum of A1 plus A2 is still in this input-output pair set. So this means we can apply the combo of BSG and PFR to get a dense subset A prime of A, such that the span of A prime is not too large. And because A prime is a subset of A, so it's still an input-output pair, but it does not consist of all the inputs. And we have the guarantee that the span of A prime is small. And so we can use the span of A prime, which is like a subspace, to identify some linear function that is consistent with this set A prime the most. And in particular, we can write the span of A prime as like a fine function which looks like x concatenated with Lx plus W, but the span of A prime is actually not a function, but a relation. like there can be many possible shift W. But because the size of the span of A prime is not much larger than the size of A prime, so we can still control the like the possible different outcomes for each input X in this span A prime. And then by doing this, we will lose an extra factor, which is like the span A prime divided by the size of A prime, but this factor is still polyepsilon. So in the end, like we go from, like we start from the set A, which consists of all the input, and then we get the A prime that has density polyepsilon, but has a small span. And then because the span is not too much larger than the size of A prime, so we get a linear function that is consistent with like polyepsilon fraction of A prime. And in total, we still get a linear function that is consistent with F on polyepsilon fraction of the input. So we are done. And so basically, I just want to use this example to show how the PFR is typically used in TCS applications. And the second important applications of PFR in TCS is the approximate duality conjecture, which says that if we have a set A and another set B, such that the inner product, so the inner product of A and B mod 2 can be either 0 or 1. And a result by Ben-Sasson, Ranzui, and also by Lovett shows that if the expected, like if the inner product of A and B mod 2 is like slightly biased, then we can actually zoom in and find a subset of A prime, and a subset of B prime, such that the inner product of A and B mod 2 is actually a constant over A prime times B prime. And in fact, and also the density of A prime and B prime is at least 2 to the minus n over log n. So like we start from two sets that only have like the inner product is only like slightly biased, but then we zoom in to find some subsets, such that their inner product are completely biased. And this lemma is turns out to have many important applications in TCS. And it's too hard to prove in the talk, but I just want to make a comment that the analysis actually needs to work for some set A that has doubling 2 to the n over log n. So for this approximate duality theorem to work, we really need like a Freiman-Ruzsa theorem with polynomial laws to get anything non-trivial. And so with the polynomial Freiman-Ruzsa conjecture proved by Gowers et al., we now also have the approximate duality being a theorem, and it actually has a lot of applications. So the original motivation of this approximate duality by Ben-Sasson and Zui is to do some analysis for two source extractors that satisfy certain structures. And this applications is also used in the recent work by Arobia et al. And also this approximate duality conjecture gave the first sublinear bound for the log rank conjecture. And although the later work by Shahar improved the bound to square root and without using PFR, this is still a nice application. And there's another application which is still the state of the art, which is the lower bound for the message side, for the code word size of matching vector codes. And matching vector code is basically a family of code, and it's the only way that we know how to construct a locally decodable code. And as a side note, for this applications, it requires the approximate duality for over ZMN, and the work by Bowman, Gavir, Lovett proved that this is actually implied by PFR over ZMN, and this is also proved by GGMT recently. So we do have the lower bound for matching vector code as an application. And there are many more applications, such as the soundness bound for testing quadratic polynomials. And PFR also implied the first non-mutable code for multi-bit message in the two-split state model, which is a nice application in cryptography. And I also want to note that actually Sanders quasi-polynomial bound is already implies some really good results. And with PFR, this it doesn't seem to give something better than the current state of the art. And another nice recent application is by Li and Zhong, which is like a linear somewhere random condenser, which is a nice object that can be used for extractor constructions. And I'm sure there are many more other applications that I'm not aware of. And I've heard about some exciting applications that are coming up. But like anyway, there are actually a lot of applications of PFR in TCS, and I'm sure you can find more. And finally, I want to make a comment about like a close cousin of PFR, which is the Bogoliubov-Ruzsa theorem. So the Bogoliubov-Ruzsa theorem states that if we have some set A that has a small doubling, then it turns out that we can find a subspace V of a large size that is completely contained in A plus A plus A plus A, like the 4 times the 4 subset of A. And it is conjecture that we can actually find a subspace V of size at least of density at least 1 over poly K, and by like just taking the constant number of sum of A. But and this conjecture turns out to be stronger than PFR, but it is still open. Like the proof of GGMT does not imply the polynomial version of this Bogoliubov-Ruzsa theorem.
So, sorry. Oh, yeah, I was going to ask what's coming on the next slide, so ignore
Okay.
this.
Okay. Yeah. So the best known bound for the Bogoliubov-Ruzsa theorem is by Sanders, which is quasi-polynomial. And Sanders actually proved the approximate version of this, which says that if we just take the 2 subset A plus A, then it already contains like 90% of subspace V. And this result have many nice applications, and I'm just listing a few here. And I'm sure there are many others that I'm not aware of. And a recent exciting breakthrough by Kelly and Mecca on the theoretic progression also implies some like stronger version of Sanders' result in some sense. Like the results show that we can actually like the results show that there actually almost that we can find a subspace V such that almost all of V is contained in A plus A. And also they also show that there exists an affine subspace V that is contained in just the 3 subset of A instead of the 4 subset. But their result, although their result improve Sanders' result in some sense, but it does not improve the size bound of the subspace. So the best non-size bound we know for the Bogoliubov-Ruzsa theorem is still the 15-year-old result by Sanders. Okay, now we finished the application of PFR in TCS, and next we will go through the proof overview of PFR by Gowers, Green, Manners, and Tao.
Sorry. Sorry, I've got a small question about the previous slide. Can you go back one slide? Yeah. So approximate BR, does that imply the BR theorem, or like is it trivial that there's like if
yeah, good question. So yes, it does imply the actual BR theorem. It's based on the pigeonhole argument by Terry Tao. It shows that if we have like say 51% of V that is contained in A plus A, then if we take like A plus A plus A plus, like if we take the four subset of A, then like it like basically it's just that we can consider every possible combination because a subspace is closed under addition. So we can take an element and consider all the possible combination of it as the sum of two different elements in V. And then one can use a pigeonhole principle to show that there exists at least one pair such that both elements in the pair falls inside that 51% of V.
Thanks.
Any other question?
Sorry, can I ask a question?
Okay.
Yes, so I'm wondering, I mean, because you say you can find sort of the subset of A, right? So is this you say it's just this subset of A? So we know how to really find this A. That is the proof constructive or just the existence of such kind of the subset of A prime?
You mean for PFR?
Yeah, and then also PSG.
If I remember correctly, there is some like kind of constructive version of PSG, but yeah, sorry, I don't remember the details and probably cannot answer that question. And for PFR, the proof is not constructive.
Okay, thanks.
Like it can be constructive in some sense, but not efficient. Not efficient.
I see. Oh, that's good. Thanks.
Okay. So the proof overview of PFR works as follows. So they use a high-level strategy, which they claim to be a really old idea by Gowers from like 20 years ago or something. And the idea is to start with a set A that has doubling constant K. And then we want to make some small operations on A to turn it into another set A prime that has a smaller doubling. And smaller means say like K to the 0.99. And then we'll repeat this procedure until we eventually converge to a set of doubling exactly 1, and this will be a subspace. And the high-level idea is that if the operation that we make on A does not change it by too much, then cumulatively, all these operations should also turn the set A into some other subspace V that is like close enough to A. But of course, this is very big, and I will talk about it more formally later. Yeah, but before we explain all the details, first, I guess we need to figure out what these small operations should be. So let's consider our first example, which is a random subset of a subspace B. So if we have a set A that has size like that is a random subset of a subspace, then we know that A plus A is exactly the subspace. So natural operation is just to take A prime to be A plus A. It seems like after one step we already done. But for the second example, which is the translate of subspace, this choice no longer works because we can see that this A plus A is also the union of like roughly 2k squared translates of the subspace V. And for this new set A plus A, the doubling of A plus A becomes in the order of k squared, which is even worse than what we start with. But it turns out that for this other extreme case, there's another natural choice called the fibering, which is we start with the set A, then we take like a random shift of it, or actually a shift from V plus Ti plus Tj. And then we consider the intersection of A and this shift A plus H. Then it turns out that if these translates are like random enough, then most of the translate will be filtered out, and we will only be left with exactly two translates, which is V plus Ti and V plus Tj. So now we also get an affine subspace, which is really good. Any questions? Okay, and then we'll continue. So we saw that there are two natural operations that we can make. And if the set A that we start with look more like a random subset of some subspace, then we can just take the next set to be the sum of A with itself. And then we will get closer to a subspace. And if A looks more like translates of many, looks most like many different translates of the subspace, then we'll take the fiber, which is A intersect with some shift of it. And we'll also get something that looks like a subspace. And the question is, in the general setting, does a general set A actually strictly improve with either of these operations? And it turns out that there is some mixed case that it does look like we cannot improve with either operation. And the mixed case is the 2 square root k translate of, we take 2 square root k translate of the subspace V. And then for each of these subspace, we take a random subset of it of density 1 over square root k. And one can verify that this mixed case actually have doubling constant k. But for this mixed case, if we take the next set A prime to be A plus A, then we will end with 2k translates of the subspace V. And this thing still has doubling constant k. So we are not making any improvement. And one can verify that by taking the fibering, we will get a random subset of a subspace of density 1 over k. And in that case, we also have doubling k, and we are also not making improvement in that case. But at least the good news is we start from a mixed case where we make no improvement in either case. And if we take the sum set, and somehow we get to an extreme case, which is the union of translate over subspace. And so maybe in the next step, we can just take the fiber and then improve a lot. And so this is the intuition of what we should do in this mixed case. It turns out that this actually works, but to me, although this works, in the actual proof, this mixed case actually comes up in a way that I didn't really expect it to show up, and we will see later. Yeah, so the high-level strategy of GGMT works as follows. We have two natural operations of taking either the sum or the fiber, and then we have a third operation, which is the mixed operation. That is if we make no improvement in either the sum case or the fiber case, then maybe we can combine the two different operations to improve a lot in one step. And the next question is how do we formalize this high-level ideas? And like Gowers had this idea like 20 years ago, but he actually couldn't make it work, so it must be something really hard to formalize. But it turns out that like there's entropic notions that can make these ideas just magically work. And I found the proof very beautiful and want to go through it in details.
Sorry, I've got another quick question. So in the mixed operation, you always take those two operations in the same order? It's always sum then fiber?
Yeah, that's a good question. So in the proof, we'll see that it actually should be, I guess we wouldn't see, but but actually it would be taking the fiber and then the sum. And it shows up like in a really weird way from the proof. And I don't have a good intuition for why this should be the case. Yeah.
Thanks.
Yeah, good question. Okay, so we review some very basic notion of Shannon entropy. So if we have a random variable x, then the Shannon entropy of x is just the expected value of log 1 over the probability of x. And the only property that we will need to use is that for some the Shannon entropy of a random variable x has is at most log of the support size of it. And the conditional entropy of x condition on y is just the exploitation of the entropy of x condition on like the fixing of y. And for conditional entropy, there is a really nice property for Shannon entropy, which is the trend rule. So the trend rule shows that the entropy of the joint distribution of x and y is exactly the entropy of x condition on y plus the entropy of y. And there's also a notion called a mutual information between x and y, which is the entropy of x minus the entropy of x condition on y. And the property we are going to use is that the mutual information is non-negative, and it is 0 if and only if x and y are independent. And one can also define like a conditional version of the mutual information, which is just the expectation of the mutual information. Okay, now let's proceed to the next slide. So from this entropic notion, they defined a measure called the entropic Ruzsa distance, which is for some random variable x and y, we take x prime and y prime to be some independent copies of x and y respectively. And this is just to deal with the case that x and y are not independent. And we will define the entropic Ruzsa distance between x and y to be the entropy of x prime plus y prime minus the average of the entropy of x and the entropy of y. So and we can consider the entropic doubling, which is just the entropic Ruzsa distance of x with itself, and it would be the entropy of the sum of two independent copies of x minus the entropy of x. And in some sense, this is basically the log of the doubling constant. And for an x that is uniform over some set A with doubling constant k, we can use the upper bound for the entropy of x by support size to get that the entropic doubling is bounded by log of the actual doubling. And this entropic Ruzsa distance has a nice property that it is non-negative, it is symmetric, and it satisfies triangle inequality. So it's actually like a distance. but it's not exactly a distance because we have that the entropic Ruzsa distance of X with itself is 0 if and only if X is uniform over some affine subspace. And so typically this is not 0. So it's not a metric. And with this notion of entropic Ruzsa distance, the high-level proof work as follows. So at the beginning, we start with the distribution x0, which is the uniform distribution over the set A that we start with. And then we have that the entropic Ruzsa distance between x0 and itself is at most log k. And the next step is we want to apply some natural operation to get x1. And then the entropic Ruzsa distance of the entropic doubling of x1 should become something like 0.99 times log k. And we'll apply this operation for more steps and reduce entropic doubling to 0.99 to the I times log k. And then eventually we will converge to something that has entropic Ruzsa has entropy doubling 0. And this is exactly a uniform distribution over some subspace V. And at the same time, we also want to maintain the fact that after we turn one distribution into a new distribution, it is still not too far from the distribution we start with. And so we are going to maintain the divergence measure tau of xi from x0. And it needs to satisfy that. So first of all, the increase of the divergence in each step is at most some constant times the entropic doubling. And also we will start with like the starting distribution x0 would have divergence like roughly log k, so that by like after the first step we increase the divergence by say log k, and then after the second step we increase the divergence by 0.99 times log k, and then if we repeat this procedure we will get a geometric sequence, but this thing is still a constant. So eventually when we converge as this distribution x star, which is uniform over a subspace V, we still have that the divergence of x star is linear in log k. And finally, you will want to guarantee that if the divergence of this x star, which is a uniform distribution over V, is log k, then this will imply that the intersection of our original set A and our final subspace V has density 1 over poly k in both A and V. And this is exactly the guarantee we want for PFR. So next we describe the operation that we need to make to turn a distribution into a new one. So it's exactly as what we described. We need to take either the sum or the fiber. And the choice of sum will just be taking two independent copies of X and add them. And it's very natural. And for the fiber, we actually have a more clever way to define it, which is X1 conditioned on X1 plus X2, which means like we read
I don't know if it's just me, but the sound itself, is that just oh.
The two copies are independent. Was that your problem?
Oh, sorry, I think that's probably a bad connection on my end. Sorry, ignore that. I'm sorry for that.
Okay, whoops. Yeah. So so the fiber case is just that we randomly sample some value from X1 plus X2, and then we consider the distribution of X1 conditioned on like X1 plus X2 equals to H. And this operation is And if we are in the case that X is the uniform distribution of some over some set, then this operation is exactly taking X and taking the intersection of X and some shift of X. So it's coincide with what we described, but like generalized to like entropic version for like distributions. And like there is a important inequality called the Freiman inequality by I think Green, Manners, and Tao, which shows that it turns out that the entropic doubling of the sum case and the entropic doubling of the Freiman case, like their sum is at most 2 times the original entropic doubling. So this means either X prime, either the sum case X plus or the Freiman case X minus will give us a better entropic doubling. I guess not necessarily better. Like it could be the case that the 2 entropic doubling are like the same as the our original entropic doubling, which correspond to the mixed case. And but what actually make their argument work is the strengthened version of this Freiman inequality called the Freiman identity. So it turns out that we can write 2 times the entropic doubling as the entropic doubling of the sum case plus the entropic doubling of the Freiman case plus some magical term I, such that if this term is small, then this implies that the mixed operation we described is actually good. So we'll see what this magical term actually means. So assuming this is true, this means if neither X plus nor X minus improve the entropic doubling a lot, then we will get that this magical term I is very small. So this implies that the mixed operation needs to be really good. And so we will pick the mixed operation in this case. Okay, now let's see what this magical term actually means. So to compute the entropic doubling, we will consider like 2 independent copies of X, say X1 and X2, and consider the sum X1 plus X2. And then the entropy doubling is just the entropy in this 3rd row minus the entropy in this 1st row. Like the entropy in the first 2 rows are the same. So we just minus the first one. And if we take an independent copies of the first block to create the second block and concatenate them, then for each row, the entropy increased by a factor of 2. And then in the next step, we will apply a new operation, which is we take the first block and then add it to the second block. And because the mapping like xy to xx plus y is an injective mapping, so by the definition of entropy, we do not change the entropy inside each row. Like it's still like 2hx, 2hx, and 2hx1 plus x2. But then we will consider, like we will use chain rule to like decompose the entropy in each row into 2 parts. We'll basically write the entropy of each row as the first block condition on the second block plus the entropy in the second block. So intuitively, the second block would just be the sum case. And the first block condition on the second block would be the Freiman case. You can see that like this, I mean, yeah, we can write the entropy of each row into 2 terms, where the first term should correspond to the Freiman case, and the second term should correspond to the sum case. And the rough intuition is we want to show that the entropic doubling of the Freiman case plus the entropic doubling of the sum case is actually 2 times the entropic doubling of the original distribution. And this seems almost like the case, like we can write down the entropy doubling of the original distribution as these like as a blue term in the third row minus the blue term in the first row. And similarly for the purple term, which corresponds to the sum case. But for the fibrin case, it's actually a little bit more complicated. So for the fibrin case, what we get in the third row is x1 plus x2 conditioned on the sum of all four distribution. But we actually, what we actually get if we take the x1 condition on x1 plus x3 and x2 condition on x2 plus x4 is the entropy of x1 plus x2 conditioned on both x1 plus x3 and x2 plus x4. And the minus term is exactly this green term in the first row, doesn't matter. But this first term is not exactly the same as the green term in the third row. But it turns out that the difference between these two terms is exactly the mutual information between x1 plus x2 and x1 plus x3. Like the mutual information between this and this, conditioned on the sum of all four distributions. So like this difference term is actually something meaningful. So like the magical term that we claim in the next slide, this magical slackness term is the mutual information between x1 plus x2 and x1 plus x3 conditioned on S. So if we consider the extreme case that this magical term is exactly 0, then we have that x1 plus x2 is independent of x1 plus x3 conditioned on the sum of all four distributions. And a magical thing that happens in the characteristic 2 case is that x1 plus x2 plus x1 plus x3 we would cancel out this x1 term and get x2 plus x3. But because we claim that x1 plus x2 and x1 plus x3 are independent, so this means like condition on this distribution S, we get that the sum of independent copies of two independent copies of x1 plus x2 equals to x2 plus x3, which is still the same distribution, which still has the same distribution as x1 plus x2. So yeah, so with this, we show that the entropy Ruzsa distance of x1 plus x2 becomes 0 condition on S. And so we are done by taking this x1 plus x2 condition on S. And this is how the mixed step actually works. Like it looks like we take the sum and then take the fiber. But to deal with the actual case that the mutual information is positive, one need to apply the entropic version of the BSG theorem. And this will imply that there is some choice of x prime such that the entropy Ruzsa distance is bounded by some constant times this mutual information. And this choice x prime actually looks more like taking the fiber and then the sum, as what Clement asked in the few slides before. Okay, so finally, like we have some divergence that we that has some property that we want to satisfy, and a natural choice of this divergence is just the entropy Ruzsa distance between our starting distribution and our current distribution. And this is quite natural and satisfy basically all these properties that we want, but there is something that is not so natural happens here because we claim that this is a divergence from the original distribution x0, which measures how different we are from the original distribution. But for the entropic Ruzsa distance, we know that the divergence is actually positive, which means to measure how different we are from the original distribution, we need to like we are already suffering from some loss at the beginning. So in my follow-up work, I found like a tighter choice of divergence based on KO divergence. And this basically satisfies every property we need from the entropy Ruzsa distance. But it has the nice property that we start with the divergence being 0. So this will save the PFR exponent by 2. Okay, finally, just mention a few words for the ZMN case. It uses similar ideas, but is much more complicated. And we don't actually get such a nice thing that happens in the F2 case. And it's still basically following the similar idea, but they would to make this similar idea work, they need to find some triplet UVW such that they are almost pairwise independent, which is measured by the mutual information, and also satisfy that the sum of the 3 distribution equals to 0, just like what we get with like x1 plus x2 and x1 plus x3 and x2 plus x3. Yeah. And there is some link-4 formalization project going on, and the C equals 10 case has already been formalized by some software. So maybe we can put more trust on this result. And the C equals A result and the PFR over the bounded torsion group is like the formalization of both these results are both in progress. So we are welcome to join to help or just see how it goes. And we'll start with open problems. So the first one is, of course, to prove the polynomial Polynomial conjecture, which is still widely open. And the second problem is what is the exact constant exponent we should expect for the case of F2N. And surprisingly, it doesn't seem to have any like non-trivial lower bound. So I'm really interested to know if we can at least prove a lower bound like K squared or something. And finally, the current bound for ZMN is K to the N cube, which would be pretty bad for the case of, say, large prime field. So a natural question to ask is whether we can improve this dependence to something like K to the polylog n. Okay. Sorry for going over time, and thank you for listening.
No, you're not about it. Thanks a lot for the talk. Yeah, so is there any question for Jyun-Jie from the audience? Or... If not, I have a couple of questions myself, mostly related to the exponents. So you mentioned you improved the exponent, and right now it's 8. I mean,
yeah.
What is the best, like the best one could hope for, and like what kind of applications do that have? I'm guessing for linearity testing that makes it like slightly that makes it better, the density. But
yes, it does improve the like the parameter for the, say, linearity testing correspondingly. And actually, if we are really care about the constant exponent in the linearity testing applications, then we can see that in the linearity testing application, we have a loss in 2 steps. And the first step is we go from like the original set A to some subset that has a small span. And then the second loss is we go from the set A prime to its span, and they give another loss. But it turns out that this entropic proof would give it actually gives a bound for the product of that 2 loss. So if we actually utilize this fact, then we save the exponent of that by another factor of 2. But for PFR itself, I don't have a good answer for what the exponent exactly should be. And as what I listed here, there doesn't seem to have any non-trivial lower bound. And a natural next step that we can try to make to improve the exponent is by proving the better bound for the entropic BSG theorem, but that also doesn't seem that easy.
And kind of related also because you mentioned that Z itself is an open problem. So is it clear there needs to be a dependence on M in the exponent for the ZNM, or like is it conceivable there could be in an ideal world, like no dependence on M at all?
I think we at least need to have some, say some factor M in the front to deal with some like some annoying case that if we actually want a subgroup, then like the size difference between the subgroup is by a factor M. And I assume that should be a natural lower bound for whatever we can get. But yes, but I think a more reasonable conjecture would be like no, I shouldn't say that. Like it should have at least some poly M dependence. But in the like in the factor in the front, but not in the exponent.
So maybe like,
so that's why I think like maybe poly log M is possible for the exponent.
Is there any other question from the audience? If not, I'm gonna stop the recording. And yeah, thank you again for the great talk, Jyun-Jie. And